Hello and welcome to our lesson on systems of linear inequalities. So before we discuss the systems of linear inequalities, I just want to give you the general concept about systems of any inequalities. We've talked about systems of equations, but a system of inequalities is similar, where the word system implies that we're looking at two or more together. So if it's a system of equations, it's two or more equations. If it's a system of inequalities, it's two or more inequalities. And what we're trying to figure out is what they have in common. What do those equations or inequalities share in terms of solutions? So we're looking at two or more equations, or in this case inequalities, that are considered together or at the same time or simultaneously. And a system of equations will typically contain one distinct solution. So a system of equations typically has one distinct solution. However, a system of inequalities can contain a set of solutions or regions of solutions that are restricted to specific locations on the graph. So we'll contain infinite solutions, and these solutions are restricted to specific regions of our graph. Now, the one solution is sort of pertaining to linear systems of equations, but for any system of equations, there are generally distinct solutions, where with inequalities, we're looking for these regions of infinite solutions. It's like when you solve an equation, just to think about solving an equation, you get an answer like x equals 3 versus you solve an inequality and you get a solution set like x is greater than 3. This is a distinct solution. This is an infinite set of x values that would work. Okay, and the same will be true when we're looking at systems of equations and inequalities. Now, the only way to show the solution region, which is sometimes called the feasible region for a system of inequalities, is to graph. It's the only way to capture all of the solutions, or at least the where all the solutions are headed for your system. So when we're going to graph to find our solution region, you're going to graph your inequality just like you would graph your related equation or function. So if you were graphing y equals 2x plus 1, for instance, knowing the y-intercept is where we would start, and the slope of 2 or 1 tells us how to rise and run. It's the same thing for a linear inequality. If it's y is greater than 2x plus 1, we start at 1, we use our slope to rise and run, but we may have a dotted line or a dashed line instead of a solid line, and of course we have to shade. So we graph the inequality just like we would graph our related equation or function. So again, you would graph y equals 2x plus 1. In the same way, you could graph y is greater than or equal to 2x plus 1, with the exception of we have to shade, right? However, when you're graphing an equation or a function, we use a solid line because every point that's on that graph is considered a solution. When you're graphing an inequality, that might not be true. If you are graphing an inequality that has your greater than equal to or less than equal to, then your line will still be solid, your graph will still be solid, because the equal to means the points on the line or your graph are still included in the solution set. But if we're looking at strictly greater than or less than, then your graph is going to be a dotted or a dashed line to show that the points on the line or the graph are not solutions. So we exclude the points that are on the graph as being part of the solution set by using a dotted or dashed line. Now, if you're graphing, again, an equation or a function, only the points that are on that graph are solutions. But when you're graphing an inequality, then the solutions are restricted to an area that's created by the graph. So in general, if we have graphs that contain a greater than or a greater than equal to symbol, we will be shading above, and I'm going to say line here because that's what we're focusing on, so we're shading above the line. And if we have a less than or less than equal to, then we're going to be shading below the line. And if we are unsure of ourselves in where we're shading, we can always use test points. So you pick a point that's in your solution region and make sure that when you plug it into your inequality that it makes a true statement. Okay, the solution region should be shaded. Again, we're going to shade this area, and that's to show that all the points that are in that area are solutions. They're all part of our solution region, or this feasible region. Okay, so when it's a system, we're going to graph one at a time, and the solution region to the system is going to be where the individual solution systems overlap. And somehow I didn't put that in my notes. Okay, I'm so sorry. The solution region to our system is going to be where these things overlap, because we're looking at the same time, what do we have in common? So let me show you what I'm trying to say. So I'm going to call this, let me use this over here. I'm going to call this the inequality number 1. I'm going to call this one number 2. And let me make some different colors here. So for the first one, I can see that, and then I did not, what? I said 2. Guys, don't listen to what I'm saying. Just know what I mean, okay? I wrote a 6 there. I'm going to call this 2, like I said. So the first one, I can see a y-intercept of 0. There's no number being added to the x, and I can see a number in front of x is 1, so a slope of 1 over 1. It tells me to start that line at the origin and go up 1, right 1 to make another point, and as many points as I want to try to make that line. Now, because we have an equal to in our inequality, we're going to make a solid line. So I'm going to go ahead and connect these. I'm going to try to connect these. That was pretty good with a solid line. And because it's less than, we're going to shade below that line. Shade below. Now, if you're doing multiple and you're doing this on your own paper, you don't want to go crazy with the shading, okay? Because we're going to end up graphing a second one here, and we're going to look for where the shading overlaps. So there's the first one. Okay, all those points that are shaded and all those points that are on that line, those are the solutions to that one inequality. Okay, so now let's look at the second one on the same graph. At the same time, we're going to compare these two in this system. So in this one, b is -5, and m is 2, or 2 over 1. So I'm going to start at -5 with a point, and I'm going to go up 2 over 1 as many times as I need to in order to make a good sketch here. And this, again, is an equal to, so a less than equal to. So it means I'm still going to make a solid line, and I'm still going to be shading below. So I'm going to try to connect those points with a solid line. And that was I tried. Let me try one. No, that was worse. Okay, 3 times a charm. I got it. Okay, well, I'm going to go with it. So there's that line. And if I shade below that line, then I would be looking at the solutions to that equation being over here. I'm going to keep shading everything below that line. Okay? Now, the solution region to the system are the points that we have in common. So, like, where do the two solution regions overlap? Or what points or what area is going to make both of them true? So what's happening in this little area is we have solutions only to the one that I have in pink. Okay. What's happening in this area is I have solutions only to the one that I've graphed there in red. What's happening in this area is I don't have any solutions to either one of those inequalities, but what's happening in this region is where the pink and the red are shaded. In this region here, and I know it goes beyond a little section of graph that I've closed in, but in this area, this is where both are overlapping. All of those points would make both of those inequalities true. So this graph and that shading is showing my solution region. So that is our solution region, or we can also call that the feasible region. The feasible region. And if we pick any point that is on one of the boundary lines for that solution region, or any point that's in that solution region, it's going to make both inequalities true. Okay, so there's our system. Let's look at another one. So again, I'm going to call this number 1. I'm going to call this number 2. So the first one, the first inequality, has a y-intercept at -1, has a slope of 2, or 2 over 1, and has a greater than symbol, so that's going to be a dashed line, and we're going to shade above that dashed line. Okay, so starting at -1, slope of 2, up 2, right 1, I can make another point and infinitely many points if I want. And now I'm going to connect these with a dashed line. and I probably don't want that tool. So I'm going to make a dashed line because this time the points on that line are not part of the solution region, and that one's greater than, so I'm going to shade above that line. So all these points up here are solutions to that first inequality. Okay. Now number 2 has a y-intercept at 2, and it has a slope of 1/3, and it's less than, so it's going to be a dashed line again, and we're going to shade below. So for number 2 here, starting at 2 on the y-axis, going up 1 right 3 as many times as I need to try to make a nice graph here. Again, this is going to be a dashed line. The points on this line are not going to be part of the solution set, and I'm going to be shading below my line. So if I shade below, now again, that shows the solutions to the one in red. But what we want when we're looking at this system is at the same time, where are the points that make both inequalities true? That is, where do our solution regions overlap, or where are both shaded? So in this area, it's only blue shading. That would make only the blue inequality true. In this area, it's only red, so only the red's true. In this area, neither one. No solutions to either inequality. But in this area here, we can see both are shaded, so all the points that are in this region are going to make both inequalities true. So that is our solution region. So this is our solution region, or feasible region. Okay, and again, you can test. Pick a point in there if you want. Like, it's very clear to me that -10, -5 is a solution according to my graph. So if I put -10, -5 in, let me just show you how this works. So I'm going to put the point is -10, -5. I would put -5 in for y, put -10 in for x, and make sure we get a true statement. So -5 is definitely greater than the -21 that's on that side. And it should work for both. So if I plug into the second one, I would have -5 less than 1/3 times -10 plus 2. And -5 is definitely going to be smaller than -3.3 repeating plus 2, so -1.3 repeating. Okay, maybe not the prettiest point to check, but if you plug a point from your solution region into both inequalities, you're going to end up with true statements. And that work just looked a little sloppy, so I'm going to let it go. Okay, let's try another. So in this one, we got this special guy right here. That was a special one. And then number 2. Number 1 is special because it's not in our typical graphing form. We don't have a y and an mx plus b. Remember, when we only have one variable in our relationship, we're going to be looking at either a vertical or a horizontal line. So if this was an x equals 1, think about a table of values. Okay, think about a table. X would equal 1 no matter what y is equal to. So this is going to be represented by a vertical line. So think about 1, 0 being a point, or 1, 2 being a point, or 1, -2 being a point. Okay, so this is going to be a vertical line. It's helpful if we can remember these things. So this is a vertical line. And it's going to be a dashed line. And the shading, okay, if we have a vertical dashed line through 1, think about this. This is the cutoff here. What we want to include in our graph would be all the x values that are greater than 1. Now I can't shade above or below a vertical line, but where are the x values that are greater? Well, we want to go in the same direction that that symbol is going, so we want to shade to the right of our line. So that's where all of the x values are that are greater than 1. So greater than 1 would be here. Okay, so greater than in this case is right of our line. Now the second one is a little more traditional, which is kind of nice. Looking at the second one, we have a y-intercept at 0 and a slope of 3 and a less than or equal to, which means a solid line shaded less than, so below that line. So we're going to start at the origin, up 3 and right 1 to make a point. Again, as many times as we need. And then we're going to try to connect those with the solid line. That wasn't too terrible. And then we're going to shade below that solid line. And so now we want to know, where do we have a solution set to the system? Where are the points that make both true? So here, it's only blue. Here, it's only red. Here, nothing. But in this area, right in here, we have blue and red. That's where we are less than the red line and right of the blue line. So this area, all of this, is my solution region. Okay, so that's my solution region. Again, pick a test point in there, plug in, it's going to make both those inequalities true. Alright, I got one more to show you. If you're feeling confident, you can try this, but I did put 3 inequalities into one graph, which is just crazy, right? So let's look at the first one. First one, we're going to start on the y-axis at -2. We're going to go up 1, right 1 to make a point. Because it's greater than, we're going to make a dashed line. And again, because it's greater than, we're going to shade above. Okay? I don't want to go too crazy with my shading, but there's the first one. Second one. Second one's going to start on the y-axis at 4, and the slope is a -1/2, so I'm going to go down 1, right 2, as many times as I need to try to make that line. This one's going to be a solid line through those points. That wasn't too bad. Solid line because we have the equal to. And greater than, so we're going to shade above that solid line. And so if it was just the 2 inequalities, again, here is only blue, here is only red, here is nothing. Right now our solution region would be here. That's where we're blue and red. Both are shaded. But we've got a third one to put into this picture. So in this third one, right, we don't have any slope. Okay, we don't have anything in front of x. So we're starting on the y-axis at 5. But if we don't have any slope, right, we can say the slope is 0, no rise. That's going to be a horizontal line. And again, that's going to be a dashed line or a dotted line because it doesn't have the equal to. And we want to be less than 5. So less than 5 would be below that line. And now we've got a mess. Okay, let's try to look carefully here. In this area over here, I can see green and blue. I can see blue and red over here. I can see blue here, so that's no good. What I need is all 3, blue and red and green. Above the red, below the blue, below the green, above the red, above the blue. And that is happening in this area right here. And that little space, you can see blue and red and green. That's where all of them are shaded. Those are the points that make all 3 in the system true. Okay? So, again, if you wanted to pick a test point, to me it looks pretty clear that, let's go ahead and do a test point. Let's see, like 4, 4 looks to be in that region. So maybe we plug in 4, 4. So let's test 4, 4. If I plug it into 1, we would have 4 greater than 4 minus 2, and 4 is definitely greater than 2. That's true. Perfect. That's what we wanted. Let's plug it into the second one. We would have 4 greater than or equal to -1/2 times 4 plus 4. That would be 4 greater than or equal to -2 plus 4, which is 2. That's true. And let's plug it into the third one. So there's nowhere to plug in an x. We would just plug in the 4 for y, and 4 being less than 5, definitely true. So I think I've got the right area. My test point worked for all 3, and so we're good to go. Okay. Now I didn't mention this earlier, but Desmos is also really great at doing this. Let me just show you. You can graph these systems. It will do all the shading and everything for you. So if you want to confirm your work, here it is in Desmos, y greater than x minus 2. There's the blue one that we did. Here, let me color coordinate with what I did. Okay, there's the blue one that we did. And then we said in red, y would be greater than or equal to -1/2 x plus 4. And let's make that the red. There's the red one that we did. Okay, and then one last one, we said that y was going to be less than 5. Oh, look, it automatically made it in green. And now you can see on the graph where all three are shaded and that their colors look a little better, but all three are shaded in that little triangle that we've highlighted. So Desmos can be used to verify your work here as well. Okay, so I think you've got enough to get going on your practice, but as always, just reach out if you need some extra help. Until next time, take care, guys.